No? That's not good. All right, well, we'll get started anyways. Good afternoon, everyone. Hello, hello. Welcome back. Today we are in the middle of our polyhedra presentation project. And so as such, most of the day will be dedicated to giving you work time together in your groups. But before we do that, I would like to share with you an example of a project that I have put together for you so you can see what a finished sample should look like, or at least one example, right? Very open-ended. The actual visual elements are not set in stone. Okay, good. Alondra is here. Excellent. All right, so let's go. That button, there we go. So I put together a sample here on the Archimedes solids, which you guys read about and investigated over the weekend. So your findings there should be summarized all here. And hang on, let me get my windows in order. There we go. And this I put together in maybe less than an hour altogether. So not a whole lot of time. Granted, it's only one person, so maybe I'm a little bit more efficient. Of course, I'm also the math teacher, so maybe I'm a little bit better at this. But just to give you an estimate there of total time spent. It doesn't take much, okay? And I think it turned out pretty nice. It looks good. I added some extra pictures here and there. And this is the minimum. It's got the basic information that you need to have a complete full credit project here, okay? So, Archimedes solid. First up, the definition. What is this thing? It's a convex, uniform polyhedron composed of regular polygons meeting at identical vertices, excluding the Platonic solids, prisms, and antiprisms. So those three groups meet all of these criteria, but because they have even more specialized relationships inside them, we set those aside as their own thing, and the leftovers are the Archimedes solids. What does all this mean? If you had to explain it to a 5-year-old, here's the simple version. 3D shape, no crisscrosses or dents, made out of 2 or more matching polygons where no point looks any different from the other points, okay? And minus the prisms and antiprisms. No point looks any different from the other point. So you can't tell that like this is supposed to be the top, right? Because it looks no different than the bottom. It still has the same 2 squares and 2 triangles come together. Right here, 2 squares, 2 triangles, boop, 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 right? All the vertices look the same. They have the same shapes coming together. There's your definitions. Some easy ways to recognize if you're dealing with Archimedes solids. They are pretty much ball-shaped, okay? Not some kind of can or tube or like this flat wedge-shaped thing, all very ball-like, some more round than others. They are very symmetrical, these guys, okay? From every direction, they're looking pretty much the same. That has to do with that vertex regularity, that each vertex is the same shapes all meeting up. You don't have some obvious side or point that stands out. They're always made of only 2 or 3 regular polygons. So if you can spot more or fewer or irregular polygons, not an Archimedes solid. In fact, there's only 13 of these guys, more than the Platonics, but not an insurmountable number. So there's an exact count. If they're not one of those specific 13, it's not an Archimedes solid. Okay? So here's some more samples here. And let's start naming some examples. So here are my required examples. I've got 3 of them here with pictures and names. We've got the truncated icosahedron, the rhombicosadodecahedron, and a truncated icosadodecahedron. And we can verify on each of these. Yes, every vertex. Here I've got pentagon, square, triangle, square, pentagon, square, square, triangle, right? I've got all the same shapes coming together. Check this one. We've got the octagon, hexagon, and square that meet at every corner there. So those fit our definition. How about some non-examples? Well, relatively speaking, the pentagonal prism shown here fits all of our criteria listed, right? regular pentagon, regular square, okay? Two types of polygons coming together. Each corner is pentagon and two squares. Here's pentagon and then the two squares. Even the bottom ones, right? They'll all be the same, except our definition specifically excludes the prisms. So that's why it doesn't fit. How about the square pyramid? What's wrong with this guy? It's got two different regular polygons, triangles and squares here. But one vertex, the apex of our pyramid, is distinguishable from the others. That is to say, we can find that this one, because it's all the triangles coming together, is definitely different than this corner down here where we have the square and two triangles coming together. You can tell that this has an orientation. There's one point you could call the top and this called the bottom. And you could flip it upside down and it would look different. Therefore, not an Archimedes solid. All right, our good old Eulers formula. Let's give this the polyhedron test. How does Eulers formula stack up? Does it apply? Let's take, for example, the truncated icosahedron. Okay, you only have to pick one out of your group to test Eulers formula on. So we'll count up the faces, edges, and vertices here. We've got 32 faces, 90 edges, 60 vertices. Eulers formula, if you recall, is v minus e plus f equals 2. That's at least one way to write it. We saw it with the, I think the f plus 2 on this side. It's okay. So algebraically equivalent, as we've seen before. Fill in our numbers here, substitute those in. 60 minus 90 plus 32 equals 2. 60 minus 90 is negative 30. Negative 30 plus 32 is positive 2, which, yes, is indeed equal to 2. It checks out. Euler's formula holds for the Archimedean solids. And then finally, some cool facts about Archimedean solids. You only needed the one, but I thought both of these were good enough to include in my presentation. I went a little above and beyond here. We've got named after the Greek mathematician Archimedes, very famous guy, brilliant mathematician. You may have heard of the Archimedes principle with regard to the buoyancy, and he's the one who figured out displaced water to measure volume and all that good stuff. He's the guy who said, give me a lever long enough, a place to stand, and I can move the whole world. So, brilliant engineer and mathematician. The truncated icosahedron, you might have recognized that picture. That's the classic black and white soccer ball setup. Okay? In addition, it's also the shape of the carbon-60 molecule known as Buckminster fullerenes. This is a super strong molecule used as the basic component for forming carbon nanotubes, which is some cutting-edge technology we're on the verge of. Maybe sometime in the future we'll be able to make more stuff out of it. We're really at like a manufacturing standstill at this point for making stuff out of carbon nanotubes, but super strong, super duper lightweight material. We'll all have like indestructible clothes and vehicles, and everything will be made out of carbon nanotubes. It'll be awesome. All right? So that's pretty cool, all from an Archimedean solid right there. Okay, any questions? No? All right, ladies and gentlemen, that's it. That's the whole presentation. That's the gist. That is exactly what you will be doing and delivering on Friday. Okay? So as a reminder for today, your goal is, well, I mean, get as far as possible, obviously. But you want to get to 2 things to turn in tonight, right? Due tomorrow, attached to Monday's assignment post, you need a copy of the project so far. Everybody needs to turn in a copy, so make sure you create a copy of the file that you have the permissions to attach to Google Classroom and send to me, and your plan of how you guys are going to finish. If you don't finish it today, then you need to tell me what's left to do and who is going to be doing what. So and so, you're going to do the pictures, you're going to add this slide, you're going to add in that slide, okay? Whatever is left, exactly the whole plan of how to finish. And then the whole thing is due Friday morning. We will then give our presentations on Friday. All right, last call for questions before I send you to the breakout rooms. No? All right, then get started. Get to work. Talk to you later.